Ready to start. In our second talk this morning, Professor Susanna Zimmermann from the University of Paris-Saclay will continue her lecture series on quotients of groups of birational transformations.
Thank you. I think this is the first time I've been introduced as professor something or other. Okay, I wanted to start today's lecture with a recap of yesterday's lecture, of Tuesday's lecture. I think I'm missing a day in the week. And on Tuesday, I introduced the circuits of program, circuits of links, and relations among circuits of links. So let me recap that in a different way than I did on Tuesday. Okay, so we have more fiber spaces. We are in dimension 2. Okay. Or a perfect field. And Mori fiber spaces are, for us, they are either del Bezzo surfaces with a peak rank 1. Okay. So in over an algebraically closed field, this is P2, nothing else. Over an unclosed field, you could have a del Bezzo surface of degree 1 of peak rank 1. So over the algebraic closure, this is a blow-up of P2 in 8 general points. But then the Galois group of K bar over K could act in a way that permutes all the -1 curves in a weird way, and you cannot contract anything equivariantly. So this could happen. Or, so you have P2, or you have a quadratic surface that we met already. So we have WZ equal to x squared plus y squared in P3 over R. And over C, you can make x squared plus y squared into xy by factorizing it. And then it's just P1 cross P1. But over R, this is irreducible. You cannot do it. And you get rho equal to 1. And the other type of Mori fiber spaces are conic fibrations, conic bundles. So these are fibrations above a curve. And the anti-canonical divisor is relatively ample. And, oh yeah, this has connected fibers. So basically, this means every fiber is a plane conic. Most fibers, a general fiber will be smooth, but a finite number of fibers are allowed to be singular. So, and a priori, the base can be a curve of genus 0. It could a priori be a curve of genus 1 or bigger. So we don't, if we do not ask that X is rational over K bar, we don't know anything about the genus. So if X K bar is rational, then the genus of B is 0. I want my curve to be smooth. If my curve is not smooth, my X is not going to be smooth either. Okay, so here, let me put some examples. So examples are over the algebraic closure of K. So if K is algebraically closed, there are just Hirzebruch surfaces, so P1 cross P1, P2 blown out in a point, or, well, they are the projectivizations of O plus O minus N. Or we had this quadric blown up in two conjugate points. So the blow up of wz equal to 0 of the quadric wz equal to x squared plus y squared. Okay, this was, so the quadric is geometrically a P1 cross P1. But the Galois group of C over R exchanges the two roots of x squared plus y squared because it maps I to minus I. And this means it exchanges the two rulings of P1 cross P1. Okay. So we have this picture. And when we put w and z equal to 0, we get x squared plus y squared equal to 0. So the 2 points we are blowing up in the quadric are two conjugate points that are 0, 1, I0, and 0, 1, minus I0. When we blow up these points, we blow them up simultaneously in order to not lose the Galois action. And then what we get is color these purple. We have the two exceptional divisors and the strict transforms of the rulings. And when we blow up, so Q is a Delbecq surface of degree 8 because it's a P1 cross P1. Okay. When we blow up 2 points, we get to a Delbecq surface of degree 6. And the Delbecq surface of degree 6 that is smooth has 6 minus 1 curves that are in a hexagon. And they are exactly the ones I drew. Okay. And now the Galois action, maybe I will put it in red. The Galois action lifts to the surface and it exchanges the two exceptional divisors. And it exchanges on Q the two rulings. And the two rulings, so these two curves, lift to these two curves, they are exchanged. And maybe what is the vibration that I'm talking about? The vibration is the 1, curves passing through these points. There's a pencil. It's a P1 of curves, and the vibration is here. So this gives us, we have picker rank 1. We blew up something equivariant. We get picker rank 2. And this is has a conic bundle structure. The relative picker rank of the conic bundle structure is 1 because I'm contracting a pencil of curves. But, so this is a minimal conic bundle, but it has 2 singular fibers. Maybe let me denote it by Y. Y over P1R is a minimal conic bundle. So the relative picker rank is 1, and it has 2 singular fibers. Another example is P2 blown up in a point of degree 4. We have 4 points in P2 over the algebraic closure, and their permuted. Let's say they are permuted cyclically by the Galois group. Okay. And through 4 points, there is a pencil of conics, okay, in the plane. So when I blow up these points, I go to the bit to surface Z of degree 5. And it has I free up the pencil because I blow up the base point of the pencil. So it has a conic bundle structure whose fibers are exactly the conics passing through these 4 points. But there are 3 degenerate conics passing through these 4 points. The lines passing through 2 of the 4. So this bundle has 3 singular fibers. So let me write it here. And so let me write, maybe let me put the P1, P2, P3, and P4 points. And then let's say Lij is the line for Pi and Pj, for I and j not the same. And then what happens to these lines? So for instance, L12 is mapped by the Galois group to the L12. It's mapped to L23, and L23 is mapped by the Galois group to L34, which is mapped to L14. And then 1,4 is mapped to this one. So we have, so the Galois group also acts on these lines that pass through 2 of these 4 points. And so let's say we have, this is our L12. L12 intersects all the other lines, but after blowing up, it only intersects L34. And then we have maybe L13. L13 intersects after blowing up only L24. And who are the remaining ones? We have L14, which intersects after blowing up only L23. And then the Galois group maps L12 onto L23, which is mapped onto L34, which in turn is mapped onto L14. So in particular, the 2 curves in these singular fibers, they are in the same orbit of the Galois group. So we cannot contract one of them without losing the Galois action. So, and we can show that the 3rd fiber is also in the orbit of is in the orbit of one of these curves. So this is just to say that while geometrically this is not a minimal fibration, over our field K this is a minimal fibration. We cannot contract any curves in the singular fibers without losing the Galois action. We have to keep the Galois action. So this is a minimal. It's a Mori fiber space. I'm sorry? See? You mean the field? Or what? So Z is this space. Sorry. It's a bit crowded on the blackboard. Yeah? Does this answer your question? No. Not quite. Do you want to repeat your question? Yes. 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 Exactly. Yes. Yes. Yeah. Yeah. Sorry for not being precise enough. Okay, so we have more fiber spaces. They're either Del-Bezzo surfaces of picker rank 1 or conic bundles minimal that have conic bundles of P1 and the relative picker rank is 1. Okay, maybe I will. Yeah. Yes, okay. Del-Bezzos, picker rank 1, or conic bundles X over B, and the relative picker rank is 1. Okay, now we have circuits of links. They are elementary transformations, very like the most simple transformations between conic bundles and Del-Bezzo surfaces. And we have 4 types of them. So at the Del-Bezzo surface of picker rank 1, you can see it as it has a map to a point, and the relative picker rank is 1. And the anti-canonical divisor is relatively ample. Okay? So So this way you can sort of unify the 2 definitions of a Del-Bezzo surface on a conic bundle. Okay. So we have 4 types of circuits of links. Okay, one is the blow-up of a point of a Del-Bezzo surface. So we have here the Del-Bezzo surface, and we blow up a point. And we get to another Del-Bezzo surface. And this Del-Bezzo surface has to carry a conic bundle structure. So an example of this would be I blow up P2 in one point, in a rational point, so in 1, 0, 0, and I get the first Hirzebruch surface. The first Hirzebruch surface carries a conic bundle structure. Or you blow up a point of degree 4, you get a Del-Bezzo surface of degree 5, Z, which carries a conic bundle structure whose relative picker rank is 1. So this is, this is type 1. Then we have type 2. There are sort of two subtypes. We have a conic bundle above some base, and we blow up a closed point on this conic bundle, and we get a conic bundle. We blow up a point, closed point, or a Galois orbit. We get, let me put the points in blue. We get a conic bundle still over the same base. And then we contract the strict transforms of the fibers of the point containing the points we blew up. Okay. So this gives us another conic bundle above the same base. And the link is the birational map induced by the composition of these blow-ups. Now, another type is when I have a beta surface of pico rank 1, and I blow up a point that gives me another del beta surface. And the beta surface has pico rank 2. And the beta surface of pico rank 2 has exactly two extremal contractions. One we have here, and the other one might be a vibration, but we already have this, or a divisorial contraction. Okay, so let's blow up. And when we contract, we will get to another del beta surface. And it has to have pico rank equal to 1 because we contracted something from a del beta surface of pico rank 2. And the link is the birational map induced by these blow-ups. Then there's type 3. And type 3 is just it's the same as type 1, but my link is the contraction and not the blow-up. Okay, so this one is type 3, and the birational map is type 1. And then the fourth is that we have a del beta surface. It has pico rank 2, and it has two conic vibrations. That are not the same. For instance, P1 cross P1 has two different conic vibrations. The second projection, the first projection. And those are not the same. So the link, is maybe is the identity map. So this is the link. The identity map in this case is considered a link because I need to be allowed to switch vibrations if I want to. I need to be able to say, I have a birational map, I decompose into circuits of links, and at some point I arrive at P1 cross P1, and then I'm allowed to consider one conic bundle or the other, and I need to be able to say this. I forgot to give an example of the link of type 2 between the Bezier surfaces. So let me do this. And it's the example from yesterday where I'm in P2 and I pick my two favorite points, one I0 and one minus I0. And I have the blue line passing through these points. I blow up these points. They become -1 curves. And I have the strict transport of the line passing through these points, which also becomes a -1 curve. And well, the Galois group exchanges these 2 points, and it preserves the line. The line is just z equal to 0, it's rational. So the Galois group preserves the blue line, and I can contract it equivariantly, and I get to a form of P1 cross P1, but now the Galois group exchanges the 2 rulings. And this is a Bezier surface that over C is P1 plus P1. And the Galois group exchanges the 2 rulings. Actually, Q is isomorphic to WZ equal to x squared plus y squared in P3. So this is a P1 has picker rank 1, and Q has picker rank 1, because over C it is P1 cross P1, but we are exchanging the 2 rulings. So this is an example of a link of type 2 between the Bezier surfaces.
I have a question. So
yes.
This example is basically the same if we replace, for example, the polynomial x squared plus x squared with any reducible polynomial of r xy, but maybe the resistant surface may not be isomorphic to P1 cross P1 over C, for example. Or that's always the case.
Over perfect fields, that's always the case. So we can, I can put my field equal to Q, and then I could choose the intersection. I could choose a set, maybe x squared plus 2y squared equal to 0. And I can do exactly the same, and then I will get to the surface WZ equal to x squared plus 2y squared in P3. And these surfaces, so I can put here some quadratic form that is irreducible. And it always has 2 distinct roots because our field is perfect. So this means that surface is always smooth, and it's you factorize the quadratic polynomial, and then you can make it into x, y over the algebraic closure. So you will always get P1 cross P1 over the algebraic closure. So Q bar, you can write it as x plus square root of 2y, x minus square root of 2y, and then you get WZ equal to xy in P2 Q bar. Okay. Are there other questions for links? Okay, so, damn it, okay, I have to start all over again. I have more fiber spaces. These are the Bezier surfaces of big rank 1, conic bundles. These are minimal conic bundles. Okay, I have links. They were like this. 1 or 2. And I have type 2. This was either a link between two conic bundles or between two Del-Bezzo surfaces. Okay. Or I had a link of type 4. Okay, and the idea of introducing rank R fibrations was that if you look carefully at these diagrams, then the top surface above the bottom is always of pico rank relative pico rank 2. So here we start with something with the Bezzo surface of pico rank 1. We blow up a point, we get something of pico rank 2. We have a conic bundle of relative pico rank 1. We blow up something, we get relative pico rank 2. We have a Del-Bezzo surface of pico rank 1. We blow up something, we get a Del-Bezzo, such that above here is Del-Bezzo, and we get relative pico rank 2. And here we have a Del-Bezzo surface that has two conic fibrations, and therefore it has pico rank 2. And now the idea was to find relations among the links. And it happens that these correspond to rank 3 fibrations. So they are either the Del-Bezzo surfaces of rank 3 or conic bundles with relative pico rank 3. And with those two, you can show that there are only, so you run MMPs with respect to some divisor of your choice from these surfaces, and you only have a finite number of outcomes. In fact, you show that there are more dream spaces. You only have a finite number of outcomes. So I write relative in case of conic bundles, because a priori our conic bundle could have k square negative, and then, or you a priori have infinitely many outcomes of the MMP, but when you look at the relative MMPs, so they all have to be over your curve, then you only have finitely many. And the outcomes are all more fiber spaces. So the Bezzo surfaces or conic fibrations with relative pico rank 1. And so even more, so if you have given a more fiber space, let's say x1 over b1, such that, so we go from x to b, and then we run an MMP okay, to x1 over b1, and we have a morphism from b1 to b. So this is rank 3. This is relative picker rank 1. And then here, somewhere the 2 is divided between here and here. There are exactly, okay, so we have options. So let me repeat the diagram twice. So it's possible that here we have, so these relative picker ranks have to add up to 3. So maybe you have 2 here, 1 here, okay? And 0 here. So this means that we contracted two Galois orbits, two Galois orbits, and we can contract them one or the other. So then we have x. We go to x2 and x2 prime, so one orbit is contracted, and then contract the second Galois orbit. And it turns out we can commute these orbits and get to x1. B1, so B1 having picker rank 1, 0 over B means this is an isomorphism. So all of these contractions are over B. B is either the curve here, or in this case, we have x over a point. And the relative picker number is 1. So this way I can combine the two things. This is all over B. Or, so another option. I have relative picker rank here or here. And then I find 2 rank 2 vibrations the following way. I'm repeating the diagram a bit bigger. And, sorry, here's the one. So I have 1 rank 2 vibration here, x over b1, and I find my second rank 2 vibration here. And so in these 2 cases, I get circuits of links, and yep. So the third option would be that in this diagram here, I have relative picker rank 0, 1, and 2 here. But B1 is a curve for a point. This is a curve for a point. These fibers are connected. These fibers are connected. These are connected. So these are connected. So the case where we have picker rank 0 and 2 does not appear in dimension 2. Can appear in higher dimension, but not here.
Somehow that you take an F-cone of X, which is a kind of 3-dimensional. In this case, you just kind of go around it, and that's your.
Yes, exactly. Yes, that's what I was going to put down next. Exactly. Yeah. damn it, I keep moving on. Okay, I'm just gonna, okay, I think those who take notes, they have put it down. Okay. So we can, you get a circle. So we have X or B, and we have finitely many outcomes of the MMP. So the X1i's or B1i are the finitely many Moore fiber spaces. Obtained from X or B. And then, I pick one, and I have exactly two rank 2 vibrations between them. Okay. And then I pick the next. So I have I ordered these already, but actually I'm not allowed to. I have now a rank 3 vibration above a rank 2 vibration. So I lose one rank, and I have here a surface of picker rank 2 over B2. So the Bitzer surface of picker rank 2 or a conic vibration with relative picker rank 2. And I can contract two extremal rays. One leads to this Moore fiber space, and the other one leads to other Moore fiber space. Okay. So I have exactly two. And then from here, I have, so from X over B to this Moore fiber space, again, I find exactly two rank 2 vibrations between them. One I already have, and there's another one. And then I repeat the story. From here, I find exactly two Moore fiber spaces. One is this one, and then I find another one, and so on. So this way, I can fill up a circle going around XB, X over B. And I heavily suggested it when I said that in circuits of links, the top surface over the bottom has a relative picker rank 2. And this means here, so these rank 2 vibrations are the top varieties, the top surfaces of circuits of links. Okay, so here, I have a circuit of link. And here, I have a circuit of link that corresponds to these rank 2 vibrations. So this picture motivates that the rank 3 vibration corresponds to a relation among links. Okay, I go around, I come back. When I come back, maybe I don't have the identity, maybe I have an isomorphism, I don't really care. And the theorem is that, okay, so circle. So this circle of links is a relation among circuits of links. And we call it elementary relation. Okay. And in fact, any relation among circuits of links is generated by elementary relations. Okay, so this means if I would write the group, the free group generated by circuits of links, the free groupoid generated by circuits of links. Okay, I'm gonna write. So in other words, so let's say Birmori of the Mori fiber space X. No, that's it. X is a Mori fiber space. So if B is a point, X is the dritzel, if B is a curve, X over B is a conic bundle of relative figure 1 and X. So let's say this is the groupoid of generated by circuits of links. Between Mori fiber spaces birational to X. And this is so it has a generating set, the circuits of links, and generating relations, the elementary relations. Okay. And in order to end, so this is the second part of the theorem, the statement. And this was proven by Corti in 95 and by Skowski in 96. This is the groupoid of birational maps between Mori fiber spaces. But maybe I should put this. Okay, this is the statement. So we have two statements. The groupoid of birational maps between Mori fiber spaces is generated by circuits of links. Okay. This is Corti and Iskowski, and then that with the generating sets, we can write the group. We have the generating relations between these generators. And these are elementary relations. Okay, and this was some years ago.
So you are considering all Mori fiber spaces where the total space is birational to X.
Yes.
And this birational map does not care about the Mori fiber spaces.
No. Yeah. No, it does not. I don't know what rank 4 vibrations correspond to. We never needed to look at them, so we didn't. Maybe, so So maybe they would give you something like spheres, and then maybe you could like compute a sort of homology of this groupoid or something. I don't know. Yeah, go for it. Oh, thank you. I forgot them. So generated by circuits of links and isomorphisms. Thank you. Yeah. And then here I have to add isomorphisms. And then maybe among the elementary relations, I have to say that if I have a link and an isomorphism, this gives me again a link. So I have to add this. Do you have any questions so far? On Tuesday, I gave I think 2 examples of elementary relations. Do you want to see more examples? I don't know if I have like more or less half an hour, so I'm not sure what I want to fill the half an hour with. Okay. But maybe I want to fill it with something else. Okay, so I want to so now I want to construct my group homomorphisms from memory X to Z2. And you will see it's part of the construction why I'm picking Z2 here. This is not such an arbitrary choice. I'm sort of forced to pick Z2 here. So what I want to do is I look at the, what is the construction? I map each link to somebody, and I have to check the relations are sent onto the trivial element. And what I focus on are, so I want to send all circuits of links to 0, except the ones between conic bundles. Okay. So let me write more. Maybe let's go with P2. I don't know yet the group, okay, but I have a link, and I send it to 1. What do I want to do? Maybe before I construct the morphism, I have to look at relations. So I want to send circuits of links between conic bundles to non-trivial elements. Okay, so So in order to construct my homomorphism, I need to look at what are the relations, elementary relations containing circuits of links between conic bundles. Because those are the ones, the rest, I send them to 0, I don't care where they go. But these I need to know about. So there's 2 types. So, okay. containing so, and the elementary relations correspond to rank 3 vibrations. So I have two options. Let's say I have, okay, so we fix some conic bundle, x1 over p1, let's say. And we have some, look at links. Now, an elementary relation containing a link starting from x1 is a rank 3 vibration. Okay. Corresponds. The 3 vibration, let's say x3 or b3. Now I have two options. b3 could be a curve or it could be a point. Now, if B3 is a point, that means X3 is still better by definition of a rank 3 vibration. And then automatically X1 is still better as well. Okay. Because if I run the MMP from a del beta surface, I will get a del beta surface. And well, the MMP that I'm running is the blow up of some points of degree of summed up degree, some points, let's say P1 to Pn. I have n at most 2. And their summed up degrees is the difference of the degrees of these del beta surfaces. Okay. This is at most 8. Okay. So this is the first option. X3 is del beta, and then obtain it by blowing up X1 in at most 8 points, or of points of summed up degrees at most 8. The second option is a curve, and then that means I obtain, so then B1, so B3 is also P1. And I obtain X3 by blowing up X1 over B3. So this is a conic bundle. So X3 or B3 is a conic bundle of relative figure rank 3. And I obtain it from X by blowing up 2 points. 3, thank you, yes. 3, yes. Absolutely, yes. So what happens is that, so I have my X3, and I go to X by blowing down, I blow up 0.1 and 0.2. P1, P1, and I blow up 2 points. Now, important, those 2 points cannot be on the same fiber, because if they were on the same fiber, then X3 would have a fiber above P1 that has more than 2 components, and that's not a conic bundle anymore. Conic bundle, a plane conic only has 2. So got, I have, this is the picture. Someone with P1 and then P2. So since those points are not on the same fiber, I don't care about the order in which I blow them up, right? I could blow down, I could first blow down P2 and then P1. And so now, when I blow up P1, the only thing related sort of to Sarkisophy is to contract the fiber containing the point. Okay. So I contract the fiber containing the point P1. This is F1 and this is F2. F1 and F2. Well, they're strict transforms, but that's it. The strict transforms. Sorry. And I can contract the strict transform first. So from X3, I can contract the strict transform and then the exceptional divisor of P1, or the other way around. So from the point of view of X3, the order of contracting this part of a fiber or this part of a fiber doesn't matter, because they're in different fibers. So I can also complete here the commutative diagram. And the same, absolutely same holds for when I blow up the point P2. I can contract the fiber containing P2. And blowing up, so from X3, blowing down the exceptional divisor of P1 and then the fiber, strict transform of the fiber containing P2, doesn't matter which order I do it, because those are on above 2 different points of the vibration. So these 2 contractions commute as well. And then finally, I can contract the strict transforms of the 2 fibers in any order I want. And I go to a 3rd vibration. And that's the relation belonging to X3. So I can only do, so in fact what I'm saying is that from X3 over P1, over the base, I have exactly 4 extremal contractions, and they are contracting the exceptional divisors of the 2 points I blew up in X1, and contracting the strict transforms of the fibers containing these points. That's all I can do. So this is my elementary relation. And so this is so just to recall, when I'm on a conic bundle and I blow up a point and contract the strict transform of the fiber containing this point, this is one of the links. It's a link of type 2. And all of these are links of type 2. And in fact, you see that there's a symmetry. So here I have the same links, type of links on different surfaces. And here I have the same type of links, but maybe on different surfaces. But I blow up the same points, just on different surfaces. Okay, so I have here I have my link, and here go up the same point. And in my picture, these are rational points, but I could do this exact picture if my points were Galois orbits of size 100 or size 200. This did not really matter in my argument. So in the picture, it's 1 point, but I could do it with orbits. So, summarized, right? My elementary relations are either relations involving only del Bezzo surfaces, or involving del Bezzo surfaces, okay, having a del Bezzo surface in the middle, or that are of this square form, where two opposite sides correspond to blowing up the same point. So, this means if I want this relation to go to the neutral element of my target group, whatever it is, I need to say that, so this link, blowing up P1, and then blowing up P2, I have again blowing up P1, again blowing up P2 is equal to 0. So that means I have something like blowing up, blow up of P1, blow up of P1, blow up of P2, blow up of P1, and blow up of P2 has to be sent to the neutral element. And this means the blow up of P1 has to be sent on something of degree of order 2. Blow up of P2 to something of order 2. So I have to okay. So let me maybe go very short. So what we did is the following. So we have our Birmori X. And what we do is we go to a free product. And then for each part of the free product is a sum of set 2's. So here are the order 2's elements. And what we do is, so we take a link, we have type 1, type 2 between the Bezzo surfaces. We have type 2 between conic bundles. We have type 3, which are basically the inverse of type 1, and we have type 4. Oh, where do we send them? So anything that is a link involving the Bezzo surfaces, I send to 0. So type 1 and 3, I send them to 0. To 0. Type 2 between the Bezzo surfaces, I send them to 0. And then type 4, they are the identity map on the Bezzo surfaces with two conic bundle structures. I also send them to 0. On one hand, because they're the identity map, and on the other hand, because they involve the Bezzo surfaces. So, and the link of type 2 between conic bundles, I send them to 0 if they involve the Bezzo surfaces. And I send them to not 0, to 1, if they blow up points that are so large, have such a large degree, that here, this surface here is not del Bezzo anymore. So I send it to 1. If the degree of the indeterminacy point of chi is at least 9. Okay. Of the indeterminacy point. So, okay. Okay.
So that's why you can't do it on algebraic.
Yes, exactly. Exactly. Yeah, I have to have points of sufficiently large degree. So I did not say what my product and my sums are parameterized by. So if you look at links between conic bundles, you notice that in order for when you blow up to still have a conic bundle, I am not allowed to blow up points on the singular fibers. Okay, otherwise I lose the conic bundle. And that means that the number of singular fibers of both the domain and the target variety are the same. Okay. Okay. So I have here over the free product, I have some type of parameterized by let me put an conic bundle here, and here an M of C. Okay. So CB of X is the set of conic bundles. Conic bundles X1, P1 of relative picorank 1. So more fiber spaces, birational to X. And I quotient out by birational maps over B1. So up to birational maps over B1. Because the links of type 2 between conic bundles do preserve, they are birational maps over B1. So the links, links of type 2 between conic bundles do not mix different types of conic bundle structures. Okay, they keep the conic bundle structure. Now, for each class in here, I count the degree of the base points of my links. So then, for a conic bundle structure, on X, or like for a conic bundle birational to X, I take MC to be, well, M, let's say. The numbers, natural numbers of at least 9. And so I send my link chi onto the one of this product. The first is the conic bundle structure. Is the link goes from X1 over B1 to some X1 prime over B1. So I go to the class of X1 or B1. And then for the class, here I pick the Z that is indexed by the degree of the indeterminacy point. C, all right, so for a class of X1 over B1, and then I have M of X1 of the class is the natural number starting from 9. just that. So C is a class of conic bundles. Yeah, maybe I could just write here N. Okay. So I tried to motivate why we end up with this construction. But let me check that this is actually a homomorphism of group weights. So I'm sending my generators of the group to some elements, and I need to check that the elementary relations, the generating relations, are sent to 0. Now check this map. So for this, I need to check that all elementary relations are mapped to 0. So to 0, 0, 0, 0, etc. Yeah.
Do you have to take also this n, and can't you just take there instead of the direct sum only z over 2?
Oh, you mean without this? I could just keep, if I wanted to, the links that have a base point of degree 9 if I want. So I could, but I can do better. Is basically. I want to do as well as I can. So I want to have as much information of the links between conic bundles. I want as much information to survive as I can. Yes, exactly. Okay, so I have, if my elementary relation does not contain a link of type 2 between conic bundles, it is sent to 0 and I don't need to care. Maybe at this point I will name my map something. Map it theta. Good. So for this is good. So I have to look at the maps at the elementary relations containing a link of type 2 between conic bundles. And we consider this. We have then I have two options. So the elementary relations corresponds to a rank 3 vibration. And it has two options. So either x3 is del pezzo, or it is not del pezzo. Okay. If it is del pezzo, this means that I obtain x3 from the domain of the link. So by blowing up a bunch of points, and this means the domain of the link is del pezzo. And I blow up at most 8 points. At most, I blow up a bunch of points, and the sum of their degrees is at most 8. And if the sum of their degrees is at most 8, I kill them. Here, the indeterminacy point of chi has degree at most 8, and I map it to 0 by theta. Well, let me remind why. So, because there's a birational morphism from x3 to x1, and then x1 is del pezzo. And the link chi, it go from x1 to x1 prime with chi, will be 1. And it factors by x3. Maybe this is not a minimal resolution, but one of the resolutions is x3. So the base point of my link has degree at most 8. Let me maybe write it again. So I have x3, I have x1, I have x1 prime, I have chi, this is over b, 1, and this is b3, this is 1, and there's a partial morphism that factors this way. So the degree of the indeterminacy point of chi is at most 8. So now in the other case, so if x3 is not del pezzo, we saw that actually it's B3 is B1, and the relation is a square. And one of the sides is our link chi. And so chi blows up some point P1 and contracts the fiber, the strict transform of the fiber passing through that point. And we saw that on the opposite side of the diagram, we have a link blowing up also P1. But maybe P1 is now on a different surface. We don't know. But the point is sent by an isomorphism onto this point. And it has the same degree. So in this relation, X, the degree of the indeterminacy point, P1, appears twice. And since I have said 2 here, my relation is sent onto 0. Do you have any questions so far? Okay, so a priori, now I have a homomorphism of groupoids. It is surjective because for any conic bundle structure, and any natural number, maybe not, depending on the field. For a lot of numbers, I find an elementary link between conic bundles that has a base point of this degree. Okay, so surjectivity depends on the field. Maybe there are fields with no extensions of degree 11. So then, okay, I cannot get 11. Now, I want to have a homomorphism from beer X to Z too. So now I embed my beer X in here. And I need to check when this homomorphism of groupoids restricts to something non-trivial starting from the Cremona group. So the group that I'm particularly interested in is the group of partial maps of P2. And I take what I do is I take a polynomial of degree at least 9 that is irreducible. So suppose we have such a polynomial. And then I can send the map xy going to x p of y, y. This is my fp, my phi p. And what I can show is that this element, so this is an element of Birmori. It's a composition of circuits of links between conic bundles preserving the second projection. And I can check that it has a non-trivial image here. And so because I can decompose it. As I go from P1 cross P1 to P1 cross P1 with phi P. Now, I can blow up the point. So it contracts the fibers given by p equal to 0. This is a Galois orbit onto the point y equal to p equal to 0. Okay. And this is so this Galois orbit, this is a closed point. I can blow it up. And contract the fiber passing through this point, or the orbit of fibers passing through this point. And I go to some Hirzebruch surface. The n depends on whether the degree of p is even or odd. Could go to p0 or to p1. And then I just go back to p0 to p times p1 times p1 by blowing up rational points and contracting the fibers through these points. So it has a decomposition into circuits of links like that. We'll go to Fn minus 1, Fn minus 2, until I get to P1. And so this element is mapped to the factor that corresponds to the vibration, the conic vibration P1 cross P1. And the first link is mapped onto the Z indexed by the one indexed by the degree of P. And the other links are mapped to 0. So I can find an element in my group of birational maps of P2 that is sent onto a non-trivial element of my product and sum. This is the 1 of P1 times P1, and then the degree of P. And in fact, what this gives me is so I can project to the factor of the free group corresponding to the class of P1 cross P1. And I can restrict this to my group of partial maps of P2. And then I get a non-trivial homomorphism to that group. So this is the construction by Julia Schneider. It is, I think, from 2019. So I want to point out that the construction of Julia is slightly different. She did not really pass by, so her construction, so what I presented is sort of the playground so that you can generalize something into higher dimension. And what Julia did is use tools that are very particular to the plane geometry, to dimension 2. And what her technique comes up with is instead of the bound 9, she gets a bound 16. And I'm not quite sure why this is the case. But I mean, yeah. At the end, you put natural numbers here, and it doesn't really matter. Okay. That's all. Yeah, that's all I wanted to say for today.